Okay, welcome back everyone for another episode of IGCSE Math ZNotes Live. My name is Devan, and I am your host for this episode, along with our expert Ivan. So, Ivan, please introduce yourself. Hello, Ivan.
Thank you, Devan. So, for those who might have missed the previous few episodes, my name is Ivan Zelich. I graduated from Cambridge doing a Master's in Mathematics this year. And today I'll be going through a new topic than what we were previously, which was algebra and graphs. Now we're going through geometry. And I guess we can get right into it. So the key concepts of today's lesson will be quite simple things like area, similar triangles, how to identify them. And yeah, I guess those are the two main topics. And we'll see an angle tracing, so going around diagrams and figuring out algebra from the given kind of geometric situation. So yeah, those things will become clear as we go on. Okay, so deep dive. Let's get right into it. So quick review of facts. So angles in a triangle are up to 180 degrees. I guess this is something we're all quite familiar with, so I won't elaborate more on that, but it's always useful to remember this. Area of a triangle is half BH or half AB sine C. So just to confirm this last formula here, so the base times the height is perpendicular height, so we'd have to draw like a perpendicular here to calculate the area, and you can use Pythagoras or things like that to figure out what that height might be. In this formula though, which is quite useful if you have an angle, you have to make sure that the angle in which you use here has to be in between the two sides that you select. So AB sine C, the angle is formed by A and B. So just make sure you do that and you'll be fine. Now, obviously, we have some classifications of triangles. So there can be like equilateral triangles where all sides are equal, isosceles triangles where only two are equal, and not necessarily the third is equal to those two, or scalene triangles where they have no equal sides. And we also have some other kind of characterizations. So a right triangle is when one of the angles is 90. These guys are really nice triangles to deal with. Acute angle triangles are when all angles are less than 90. So an equilateral is one example because all angles have to be 180 on 3 because all sides are equal. So 60. And obtuse triangles, well, one side is greater than 90. So yeah, that's the simple classification of triangles. Okay, we can now move on to, I guess, a more complicated polygon, which is quadrilaterals. These guys have a bit more complicated classification because you have one more side. But the angles in a quadrilateral add up to 380. If you want to figure out in a pentagon, you just add 180 and then 180 each time, and that kind of gives you your formula. So if it comes up, just remember that. Area in a quadrilateral is base times height. So generally area is base times height. However, we have to be kind of clear about what we mean by height in each cases. So to calculate the area of this rectangle, just this side, the length times the width. This is just width squared or length squared because it's a square. Rhombus, so this is a bit trickier, and I'll give a little formula for that as well. And we have this parallelogram. So rhombus, basically all sides are equal. So it's like a parallelogram where all kind of opposite sides are parallel. This happens the same thing in the rhombus, but all sides are equal as well. So it's like almost the rhombus, the square version of a parallelogram from a rectangle. Trapeziums, so they come up quite often. And we'll see an example of that where we calculate the area of it. And so we'll see a formula as well. And kite. These guys basically have two sets of kind of isosceles triangles on each end, and I believe the formula for area is actually quite similar to the other two anyway. So to calculate the area of a parallelogram in general, we use more the diagonals in this case. So we'll see how it works, but it is a quite useful formula. So we would need this angle between these two sides, and we label these little edges here, so D1, D3, D2, and D4. And so we can kind of derive the area of a parallelogram by using our formula for the area of triangles. So we got a half. So in this diagram here, we have D1 times D2 sine A and half it. That gives you area of this triangle. And then you keep doing that, and you add them all up. I believe I made a typo here. It should be half, because when you add them, you still have the half. So the half I accidentally didn't put in. But basically, we use sine 180 minus A is actually sine A. And then we add them all up, and we get this. So the area of a parallelogram should be a half of the big diagonal D1 times D2 sine A. So you can use that if you'd like as well. If you somehow have the diagonals, that might be a useful formula to use to calculate the area of a parallelogram. But there are other ways to do it.
Yeah. At IGCSE, it's mostly base times height. The base of the parallelogram and the height of the parallelogram usually. But this is another
exactly.
So, area.
Yeah. So I just thought I'd put it in because if you're given the diagonals, then it's just so quick to do it, right? But yeah, we'll see how you can calculate it other ways. Like if you want to calculate another way, you'd have to drop perpendicular there and do base times height. Kind of the same idea. Okay. So similarity. So this is quite useful, and it comes up in a problem later as well. So we'll just talk about it a bit. So similarity basically means that this triangle here is formed from this triangle either by translation, dilation, by making it bigger, and rotation, kind of your key kind of Euclidean figure out how they're similar. But in general, if the angles are the same, the two shapes, in particular with in triangles and polygons in general, and of course they could be, because if you could make it bigger and they would still be similar, but you have to make it bigger in a particular way. And this is kind of what's being represented here. So you can resize triangles and this teardrop shape and whatnot, and they'd still be similar. They'd still preserve their kind of overall shape.
Ivan?
And we'll see more examples of that later.
Yeah. Ivan, can you do a quick...
Yeah, so here are the kind of some rules. So as I mentioned, you can flip, turn, and rotate them, and that would be called congruency. So congruency is kind of when they stay the same size, so the lengths stay the same. So for congruency, we'd actually not only need angles, we also need lengths to tell us are they actually the same. So as said here, angles and lengths must be the same, and there are rules to kind of make sure that they are. SAS. So you have two sides and an angle. That would make sure that one and the angle between them, that would mean that the triangle is congruent to the other triangle. This right here, 4.5, and identify them, then you know it's congruent. The right angle hypotenuse side rule, which is really related to Pythag in this case. Because if it's a right angle already, then all you need is to show that the sides are the sides are the same, as that's what we need for congruency, and so you would use hypotenuse and a side, and then the Pythag gives you the other side. but really it's just a reflection of rule 2 here. So it's a special case. For the third one, ASA, so if you have two angles, then the third angle is the same, and if you have one side that's the same, then you know that we have congruency. Okay, and so yeah, that kind of simple concepts, but you need to be able to identify what are the equalities in each case and to see whether it's congruency or not. Okay,
Yeah.
so we've gone through the key concepts, and now we can go through some problems. Does that sound good, Devon? Should I elaborate anything more?
Not really. It's just that when you're at the similarity slide, you just had connection problems. If you want to have a quick review,
Yeah.
it's fine.
Okay. Okay. Cool. Sorry about that, guys. Trying off a new system, so hopefully it's better than what we were using before.
Sorry about that, guys.
Okay. So here we have a question. We have a triangle and we have an angle here, and we're trying to figure out what is x. So we have to do some kind of angle tracing, as I said. So of course we are dealing with a triangle, and we have two equal sides. So the first thing we do is label that we know that this angle is the same as this angle. So we do that, and we know that, of course, the sum of angles in a triangle is 180. In particular, we have that this angle here is actually an exterior angle. And so since if a plus b plus c equals 180, then a plus c equals 180 minus b. 180 minus b is essentially this angle. So x plus x is 50, i.e. 2x is 50 and x is 25 degrees. So make sure you keep the right units. Obviously, I didn't do that there, so I might lose a mark or something. Okay, so I guess that was quite straightforward, but always useful to remember exterior angles, and that the exterior angles sum up to 360. I think all the exterior angles add to 360. And that works for actually, I think, in general, the polygons as well. So that's pretty neat rule. But anyway, in any case, the exterior angles is a nice way. If you have this angle there, then you know the two opposite angles add up to it. So it's just useful to remember to be quick.
Yep.
Okay, so there is a perpendiculars, because we have two little around here, and they're right triangles.
Ivan, can
so
you
we can
repeat that?
Yeah, so we drop the perpendiculars here, and we have two little triangles lurking on the sides there, and we have a rectangle here in the middle, and so we're going to add all these areas up. So we have to just use some information first. So this, because it's a rectangle, this side's 7 here, and because the total side is 11, we have 7 plus x plus y is 11. So y equals 4 minus x. And then we have to find the total area. So it's base times height on 2 for these triangles. And it's just base times height for the rectangle. So base times height would be 5 times 7. We also have 5 times x on 2 for the left triangle, and 5 times 4 minus x on 2 for the right triangle. When we add them up, we just get 5 times x plus 4 minus x, so x plus 4 minus x there, x plus y, on 2, which is just 5 times 4 on 2, which is 5 times 2. We have 5 times 7 here as well from the rectangle, and we add them up, and we get 45 as the total area. So the general formula kind of is, you prove it exactly the same way. So it would make sense that the general formula comes up as a plus b on 2, where a is this length, b is this length, times h. So in this case, a plus b on 2 is 9, 7 plus 11 on 2. So 5 times 9 is what we're looking at right there. And the reason it comes out is because if you look at these little two triangles, they can be kind of combined into one larger triangle there with a right angle here. That is your height, and x plus y will add up to a whatever your longer length is, b minus a, or a minus b. And then you sub that in and you add them up, and you can get that the general formula for a trapezium is a plus b on 2 times h. Okay.
Yep.
Was that all good, Devon?
That was clear.
Did I
Yep, that was
cut
really
some?
clear.
Okay, cool. Awesome. So next problem, we actually have a trapezium again. However, we have we're not asking for area, we're asking for some angles. So to find the value of x. In a trapezium, of course, these two main sides are parallel. So we can use some rules here. In particular, we want to use the supplementary rule. So this angle plus this angle have to be 180. We add them up, we get 97 minus 3x plus 69 plus 5x is 180, or indeed 166 plus 2x is 180, or x equals 7. And that's that. So it's pretty straightforward. Just use a simple rule and use some algebra, because we're doing algebra for a while. We should be comfortable with this stuff.
Yep.
Okay,
Let's
and
move on.
finally we have this kind of last problem. So this problem is we haven't really covered the key concept we have in a sense. We have similar shapes, so we haven't talked about what similar shapes means in terms of areas. So I'll just kind of try to explain what the intuition here is. So we can put this kind of shape on a grid, and if we're making it smaller by some kind of factor, this is what similarity is doing, but preserving the overall shape, then what happens is that this grid kind of gets smaller, right? And the way it gets smaller is if you're dividing by 3, if you divide every side of a rectangle by, say, 3, then you're dividing the area by 3 times 3, which is 9. In this case, it works exactly the same way. So if this 17 got made into some number like 10, so if this was now 10, say, for example, then you have a ratio 17 goes to 10, and the areas go by the square of that ratio. So having said that, we have then this formula. So in general, when you divide by the lengths of two similar triangles, and you find that ratio and then you square it, you'll get the ratio of the areas. So this is what it's saying here. So I'll call this width 1 because it was just easier to call that. So width 1 is x. We're going to label that x. And width 2 is 17. And area 1 is 159.5 and area 2 is 295. So we divide them out, and we can then solve for x. So x on 17 in brackets squared is 159.5 on 295. Then square root that and multiply by 17. Of course, we don't take the negative in this case because it wouldn't make sense. And we get x is about 12.5 centimeters. Now, Devon, should they put 2 decimal places or just 1 in this case? Because we give him 1 here.
In this case, it's I would say 1 decimal place, because that'll be counted as
1.
3 significant figures here. Yeah, it's counted as 3 significant figures. That's why.
Okay, cool. So yeah, put then 12.5, and that makes sense because we're given 159.5 there. So yeah, awesome. Yeah, and I think that's basically it. So did I explain everything I needed, Devon? Or
Yeah, I
anything
think
we should
you've
go back to?
explained everything for this topic.
Awesome. Okay. So to wrap up, well, we dealt with some kind of key concepts such as congruency, similarity. The last problem required us to relate similarity of shapes, polygons with the area, and that in general is the ratio of similarity, the area gets ratio squared. So if your figure becomes 3 times bigger, then the area is 9 times bigger. We also saw congruency. We didn't do specific tests with congruency, but that might come up later. Always good to practice those kinds of problems to recognize which shapes are similar. And yeah, and I guess that's it. That we reviewed some key concepts for triangles, and yeah, anything else I should add, Devon?
Yeah, that's it. Another thing we should add is we did for the similar shapes for in 2D because it also happens in 3D in IGCSE. So that means that you have to cube it instead of squaring it.
Yeah. Of course, yeah. I should have said that, but yeah, the way you can make sure that you're not wrong is you when you are multiplying by some factor, you'll end up with centimeters, and to get volume, you need to get centimeters cubed, so you need to cube it. But the same principle applies. When you're doing volume, you can make it into like a little grid of cubes, and that when you multiply all the lengths by some number, you get that the volume gets cubed. So definitely make sure that you cube it if you're dealing with volume. So an
Yep,
area, square it.
that's correct. So I guess that's it for today's episode. Actually, yeah. Okay, so
You there, Devon?
yeah, I'm here. Yeah, I think you're
Yep.
still having the connection problems
So I
right
think
now.
we're
So
done.
yeah, we're done. So thank you everyone for watching today's episode, and thank you Ivan for being with us today. And don't forget to check out our website, our Instagram page, and also join our Discord in the screen. You can see the link there. And we'll see you next Wednesday. Yeah, next week Wednesday. So thank you
Yep.
everyone for joining us. Goodbye.
Thanks, everyone. See you next time.